So should we wait for one more minute or should we start? I expect one more person at least. Just let's wait for 30 seconds. Yeah, never mind. Let's start. So the first question is related to parameterizations. Okay. Parameterizations are absolutely important. Now, I'm not going to give you the context as to why they are important from the perspective of mean value theorem, but let me just define it because those who are not there in the previous weeks at least know what this is. So parameterization of, I'll just start by saying parameterization of sets in R2. Okay. So let S be a subset of the plane. Okay. Then how do you define a parameterization of S? Anyone would like to do that? Parameterization of S. So S is a subset. It may be a good subset, bad subset. So let's say it's something that looks like this. And let's say it goes on. Let's say this is what S is. Okay, this is S. Then what is the meaning of parameterization of S? Or what did we mean it to be roughly? That we need to know so that even those who have not were not in the class previously, parameterization word itself, parameterization of a circle, and yes. Absolutely, absolutely, yeah. But then what is the meaning of, but then how do you define parameterization of a general set in R2? That was absolutely the context. But then if you're given a set S, what is the meaning of parameterization? So parameterization for us is simply, get this, is simply a function, okay? Basically, we want to describe S. So the idea is we want to describe S in a more dynamic way by 1 degree of freedom. That 1 degree of freedom is not necessary for definition of parameterization, but we want to give a more dynamic movement, so as a function of time kind of, and 1 degree of freedom. Remember, it is sitting inside 2-dimensional space, but still a curve can be, the feeling is that, yeah, this is like a 1-dimensional object in some sense, whatever dimension means here. 1 degree of freedom. This is what we want to capture. So yeah, so parameter. So just to formalize that in the language of mathematics, basically parameterization of S is a function f. One can and one should put some conditions like continuity and differentiability. Let's put differentiability from A to B, or that doesn't matter. We can just, but let us just put A to B, okay, for some reasons to come. A to B to S, okay. F is differentiable, number one. And the other things that I would be requiring is, can anybody tell me what should be the other most, like, absolutely necessary condition here? Differentiability is not necessary. It's not necessary. It's a good condition, but it's not necessary. But what other condition should be put on F? But that's again, suppose we have already put that. We have put differentiability, but just a more set theoretically basic condition, a more fundamental condition. Continuity and differentiability are not fundamental conditions. No, that's least fundamental, and that is not even, no. Surjectivity. I mean, if it's not surjective, then it doesn't make sense to say that this function parameterizes S, right? I mean, you must surject onto the image. So remember, this is a function from from a subset of R to a subset of R2. Remember, this is a new kind of function. Even the word differentiability has to be parsed here, because in the high school definition, differentiability is not defined for functions from R to R2. But you can take the obvious definition, okay? That both the components should be, but all that aside, most important thing here is surjectivity, right? I mean, if your function is not surjective, then what I mean, if you're parameterizing a circle using theta, and if it's not, if the image is not the whole circle, then what are you parameterizing, right? Then you're not parameterizing the circle, something else. Okay, so this is a important condition. I'll put another condition. Okay, so for the problem that I'm going to present, for problem that we're trying to discuss, we'll put another condition. Okay, and that is F is injective. Okay, I'm putting this condition for this particular, for the purposes of this particular problem. And remember, F would be something like F1 comma F2, right? It would be basically be two functions, two differentiable functions, right? Because the images are two. So here is a very basic, very basic question. Can F be injective for S on the right, for S as drawn? This is a no-brainer. Yeah, why? No, but this is not your typical function. So remember, see. So the domain of the function is not here. This function F. So maybe this. Give me 1 second. It is possible. Anyways, this is not the graph of the function. Remember, this is not the graph. What you're seeing as is not the graph of the function, as is usually the case, right? This is a different situation. That's why I'm spending time. This is the image. S is only the image. The function cannot be drawn like this. Okay, that is the strange thing here. Not strange, that's in the definitions. The thing is that A comma B, the domain is somewhere here, and F is mapping it like this to this plane. So it's a very different situation than usual. Okay, it's a very different. This is not the graph of a function. So the question is, for the kind of figure that I've drawn, do you think F can be an injective function? So remember my function, my image, my set is sort of self-intersecting, right? It's going and then it is self-intersecting and then it is self-intersecting again and so on. Yeah. So, well, what do you guys think? You are going to travel on this parameter from A to B, and here you are going to travel on S like this, and then you're going to come back and visit this point again, right? So intuitively, doesn't it seem like it should not be possible? Intuitively, I'm not saying that's a proof. If you have a continuous and differentiable function that is, let's say, starting at A. So at A, let's say you map this to this point. So let's use a different color. Let's think about this, right? This maps here, right? Now, as you're moving along A, you are moving along this curve and you pass through this point. And then as you move further, you pass again, and then you move. Then you have to pass through it again, right? Intuitively, at least it seems like, because the function is continuous. What do you think? Any opinions? Oh, yeah. So it does seem like it is not possible, but it's not simple to prove. No, but it is not simple to prove. Well, the reason why it is not simple to prove is it? Yeah. Why do you think it is not simple to prove? Well, the problem is that how do you define, how do you mathematically define or mathematically point out the fact that this curve has a self-intersection or this curve has a loop? You see, to point that out mathematically does not seem a trivial job, right? Some curve has a loop. How do you let mathematics understand that? You understand that by looking at it, but it's hard to encode that, right? So you need further language. But I mean, at least I think so. I know I might be in for a surprise if someone can actually prove it. But the point is, you don't know what you will be proving actually, right? But no, but more language is needed for this, as far as I can understand. Mm-hmm. Yeah. Uh-huh. Yes, but how do you use the fact, how do you encode the fact that this curve is having a loop like this? Unless you encode that fact, you will get, yes, it is injective. It can be injective, right? You have to strongly encode that. I mean, the general recipe, you're saying that's a general recipe for proving injectivity. But it's hard to encode this fact that it has a loop. You see, that is not easy. Okay. So unless we set up a language for that, you can't, because you don't know what you'll be proving. You will never get no as the answer. I mean, mathematically, intuitively, it seems yes. But at least the sense of parameterization tells us that, yeah, it should not be possible. But let me ask something which is can be proven. Okay. So let us assume injectivity, but maybe you guys can think, if you can think of some reason. So yeah, so that's why I will avoid such curves. Okay, I will avoid such curves naturally. So this was just so that you can understand why I'm taking simple curves. So I'll be taking simple curves, which means that it will not be self-intersecting. Okay, so it will not be the graph of functions still, but it will not be self-intersecting, maybe something like this. Okay, so this is my S, and for this I have a function f from a comma b to s, and it is a bijective differentiable function. Okay, so this function f is called parameterization. F is called a parameterization of S. There can be many parameterizations. Here is the problem, okay? Without any context as to how I came up with it, but still, the problem is f is, let's say f is a parameterization. Let's say that G is another such parameterization. Another such parameterization of the same thing, okay, of same S. So you have two different parameterizations of S. And you can imagine that is certainly possible, right? You may traverse the set S in, at two different speeds and so on. Okay, that's certainly possible. But let us keep it very narrow and try to just focus on the problem. F and G are two such parameterizations from A to B to, so G is also here. Okay. What can be said? This is a question. What can be said about FA, FB, GA, and GB? These four endpoints, right? I mean, these two are endpoints of the curve. Well, endpoints by definition, this I'm calling this endpoint f of A and f of B. And this is another set of endpoints, right? Via a different parameterization. What can be said about the relation between these four things? Is there any relation? First, let us make conjectures, then let us try to prove. So you have two different parameterization, and so you have two sets, two pairs of endpoints. What should be the relation? What do you conjecture? Yes, exactly. So the whole point is we have two different parameterizations, and we are basically asking how different can they be? Okay, two different parameterizations of the same set, obviously. Mm-hmm. Does it make sense to use? Intermediate value theorem, well, yeah, you can certainly use, but for that you will need a function from R to R. These are functions from R to R2. But what is the conjecture? But geometrically, what do you think? That is, then only we can use the tools to. This will come in, I think, later. But first, what is the conjecture? Well, it's a very simple, it's a very obvious conjecture to make. Think about it, right? Roughly speaking, FA should be this point and FB should be this point, right? Well, again, we don't have a proof for that because what does this point mean, right, for a general set S? But still, right, intuitively, that's what it should be, right? It should be like these endpoints. But then if GA, so suppose, or let us just say that this is FA and this is FB. Let us just say for a second. Now, point out to me, where do you think G of A can be? Can G of A be somewhere in the middle? Can G of A not be? So this is the question. Is it possible that G of A is neither FA nor FB? Do you think that is possible? Do you think the GA can be here? Just use your intuition. So this, okay. Anyone else? Because G is again a parameterization. So G starts here. So suppose G starts here, okay? Then as the values, as the input values increase, let's say G moves like this, and it moves like this. Now G cannot come back. G doesn't have that opportunity because G is injective. So if G cannot come back, then G has to go and has to stop here. But then how will G come to these parts of the set? It will not, it cannot. Well, that's not a proof. Again, it's not a proof, we'll prove this. But this is the intuition behind making this claim, that it is not possible for GA to be different from these two. Does everybody see that? This is how conjectures are made, right? I mean, this is some very simple stuff. I mean, for us, it is okay, but it's good enough, right? Starting with these things. But you get it, right? Does everybody see that this is not a bad thing to conjecture? Parameterization cannot just jump, right? That's why we have put these conditions of continuity. And it cannot come back. That's why we have put the condition of injectivity, right? So yeah, so the conjecture here is then that G of A is either, I mean, I could write this as an equation also, but G of A is either F of A or F of B. Does it sound okay to everyone that this should be true? Now we will do a proof. So proof. So this is the problem. If this sounds counterintuitive, then please tell me. So yeah, so basically we are proving something very fundamental, that if you take two different parameterizations, you can take two different parameterizations, two different speeds, but the starting and ending point will either be the same or swapped. Yeah. But it cannot start from the third point. This is the conjecture. This is the problem. This was a little bit of a intro to that. Again, why I was interested in this is for something else, which I will be discussing later. It's mostly in complex analysis class, not in this class. But yeah, now maybe we can try to use these things and so on. So remember, f is a bijective function, g is a bijective function from a comma b to s. Both are bijective functions from a comma b to s. No, we have to prove it now. We use the intuition to come to the conjecture, but now we'll have to prove it. Right? We will prove it from the very rigorous proof. Yeah, intuitively this is the conclusion, but now we need to prove it. Okay. Mm-hmm. Okay. Okay. That's right. There is no, because these are unknown functions. Okay. Mm-hmm. No, f of a and f of b, I am calling them endpoints because it makes sense to call them endpoints, but they are not endpoints because there is no such thing as endpoints. Right? This is just drawn for a visual representation. Yeah, that's all. Because there's no, because a curve may not look like this, you know, you may not be able to draw it. So it doesn't make sense. Yeah. But point is, what does between mean? And what does end mean? There is no, those things are not meaningful, right? There is no between and so on because it's a curve. I mean, you don't know how bizarre it can be. Intuitively, it makes sense it cannot be in between, but the point is, what does between mean? Right. I mean, it could be, it could wiggle here infinitely often. I mean, without intersecting also. And you don't even, we won't know what between means because a curve cannot be seen like this. This is just a model that we are drawing. I've just drawn this picture for reference, but the question is still valid, right? That you have f of a, f of b, and you have g of a, g of b, and you want to show that g of a is either equal to f of a or f of b. But the word endpoint is a little, has to be qualified. So I can define this to be endpoint. I can call it, I can make that, I can call it endpoint, but whether it is here or here, that I do not know. Yeah, intuitively it cannot be, intuitively it should not be here, but what does this mean for a general picture? There is no definition for that. That's the problem with this question, right? It's because of such a strange thing. It's a function from R to R2. So how about how about somehow reducing this question? So maybe that can serve, we can try that approach as well, apart from this contradiction, which is also there, possible. How about we want to put the third axis? No, you can put the third axis, but then what? What will you do? That is the question. Two points. If we take three axes, okay, you can, what will be the model of plotting? Well, the other thing that I was having in mind also is that how about reducing it to reducing the problem to R to R, something like that. G of A, we cannot write in terms of F of A because they are not, like, we don't know the relation. But really, if you want to make this a function, so see, from the interval A comma B, you are going here, right? And then G is also doing the same thing, okay? But but if I want to, instead of working with functions from R to R2, I can instead do, I can come back. I can consider G inverse, right? G inverse will be a function from S to A comma B. And it will also be continuous and such. So let's think now. Because A comma B has an order, right? So in A comma B, we can say what are the endpoints. A and B are endpoints. we can define what, I mean, we know what it means for something to be somewhere in between. We know these concepts, order and everything is there. Whereas on this curve, it's not there. So that's why when you have two objects of the same kind, you know, considering the inverse of the other, one of them can be very useful technique. Any ideas? Yeah. Then we get this, and then it's natural to consider this. This is a function from a comma b to a comma b. What can we say about this? See, this was initially a problem in from R to R2 and so on, but now it seems to have come down to, you know, more familiar place. What can we say about this? F of G inverse or G inverse of F. Certainly, right. And what more can we say? And by the way, this is not the only approach. Okay. In fact, I was first trying it with some other tools which did not work. Like there's something called connectedness, but again, that's something which is more language, which is not good for us right now in this class. Okay, so let me do that first. Yeah. So basically, see, f is a function from a comma b to s, right? So f is from a comma b to s, and g inverse. What is g inverse? Now g inverse is a function from here to here. So I simply compose them. I've composed them so that, you know, everything is from a comma b to a comma b, because now I can, because we are feeling that there is this middle thing, right? That this should be f of a and f of b are endpoints, and so if you can concretely prove that, then g of a, g of b should also be endpoints and so on, but we're not able to prove it. That's why we're coming to this situation. That's all I've done. Yes, Shyam, your question. Okay, so that is the inverse of a continuous function, right? That is the inverse of a continuous function. So, but you're right. Yeah, that is, no, you're right. It's actually not always true for R to R also. Yeah, that is also true. Yes. Bijective is there. No, that is certainly there. It is bijective, but his question is correct. How do you rigorously prove? But you see, if you just write inverse of a continuous, inverse of a bijective continuous function is continuous, you can state that. Yeah, let's not rigorously prove that. Yeah. So I'm just using the fact that inverse, I mean, we can prove it, but then we will again get into some epsilon delta arguments. Inverse of bijective continuous function is continuous if domain is a closed interval. In general, this is not true actually. Yeah, but what happens is that when the domain is a closed interval, okay, then the image is also what is called a closed set, and then it becomes something and something. Yeah, but this is something that you can assume that if, yeah, that's fine, that you can assume that the inverse of a continuous function is continuous. That's right. That's right. But in this case, it's a little, the range is a little different, right? The range is a little weird. So that's why to prove it, But sorry. It's actually, I can just say it in a very simple way, right? You're right. I mean, what you said gave me an idea. Very simple. See, it's two functions, right? Basically, I'm trying to say that both of them are continuous, right? So if both of them are continuous, you can obviously show that their inverse is also continuous, right? That's just a simple. That's of R to R. Let's just break it down to the case of R to R. And so this is continuous, this is continuous, both are bijective and both are from A comma B to R. And so, their inverse will be continuous. And so you get it, right? That's very simple. Yeah. So they will have these inverses. I mean, compositional inverse. And yeah, so then you can just compose in. Yeah, you can basically just break it down to the case of R. Yeah, but in general, this is a little tricky theorem to prove. But here it's still components are there, so it's fine. I was thinking of general metric spaces. Anyways, that's fine. Now what do we do? But that is right now. That is correct, because you see that is now G inverse F. Now this is very simple. G inverse F is, as you're saying, G inverse F is just a function, bijective continuous function. So what can we say about G inverse F of A? Well, first of all, this means that it is increasing or decreasing, right? Let's assume increasing without loss of generality. I mean, everybody knows this, right? Bijective continuous function will either be increasing or decreasing. For that, you need to use the intermediate value theorem, but that's a standard. It's a standard fact, right? Continuous and bijective from A comma B to A comma B, it has to either be increasing or decreasing. It has to be monotone, right? So that's right. So if it has to be a monotonic function, so let me write that maybe. Now I think we're getting closer, is monotonic. Since it is monotonic, so what can we say about G inverse F of A? So this will either be A or be B. Is that right? Or otherwise it has to be B. Otherwise it's the opposite, yeah? So all these, you see, all this combined in R, it becomes so nice, but in R2, it's not. So that is you see, R has an order, which makes everything work, right? And now the problem, I think, is done, right? Because you can just do G on both sides. F of A is G of A, or F of A is G of B if you take this. You can just compose by G on both sides. Simple. So such a intuitively, so this is a fact that physicists, anyone, I mean, a little bit of math of physics they've done, they can make this conclusion, but the proof is in mathematics. Yeah, the proof we cannot really give by physics. Tuition. You have to do like this. This is not the only proof. There are some better proofs using connectedness that, but this is good enough for our purposes. Okay. So I like this example, and this is also an original question, so it's good. Yeah, this came in the context of some integration of vector integration along a curve of a vector field, and so anyways, that we'll discuss later. So that was the first question. Let us are there any doubts with this question? Okay, yeah, let us now the rest of the, yes. Yes. So in general, you see, if h is a general function from, let's say, 0,1 to 0,1, and it is, bijective, continuous, then you know that h is monotone. That is okay. But now you see, if h is monotone, what can h of 0 be? If h of 0 has to either be 0 or 1. That is the claim. Do you see why? So that's all. That's all I'm saying. Yeah. Yes. If because if h is an increasing function, yeah. Okay. So these are simplified. Okay. So now the rest of the question that we will do, we will not do them to completion. Okay. We will do them partially, and you'll have to think. The next question is about polynomial parameterization. Polynomial. So whether it is possible to parameterize a curve using polynomials. That is what the question is we are interested in. So what we are interested in, you see, you take a set S in R2. Okay. Then, or for this particular example, I think I'll need R3. Then the parameterization means basically that you have a function that's something like, I'm now writing it in a slightly different language, but you can see it's the same thing. Yeah, I'm basically looking for this. Now this I can call my function f, right? This such that this domain is 0, 1 maybe, and the range is R3, well, not R3, S, whatever, S. Okay. And the question now we are interested in is when can f, g, or h, when can f, g, h be taken to be polynomials? Then the situation is much better, right? Taken to be, if it's possible. Obviously, I have yet not given any s, so when I give it, then you. But this is the question, okay? That is it possible to consider polynomials instead of arbitrary functions? Okay, so S is here, and can you cover it with polynomials? So here is a set. Okay. Wait, let me just, I know it in one form, but I had written it in a more interesting form, which let me just find it if I can. Otherwise, I'll just say the boring form. Yeah. You tell me, is sine a polynomial? Sine. Yeah, but that's not a polynomial. Yeah, but that's not a polynomial. That's, yeah. No, Taylor's polynomial is a different thing. Taylor's polynomial is a polynomial, but Taylor's series is different, right? They are very different. They are not very different things, but they are different things. Okay? So basically, Taylor's polynomial Pn is a polynomial, right? For a function, for a function f, Taylor's polynomial of nth degree is like the best polynomial of degree n, which can approximate f, right? And then when n becomes larger and larger than the limit of these polynomials, whatever that means, that is called the Taylor's polynomial. That's called the Taylor series. Yeah. Okay. But there are definitions and such. Anyways, yeah. So I can't find the good version. So here is a set. Okay. Here is a set T. Sorry. Here is a set which is. I should have prepared this better, but in any case, this is the set. We have T cos T, comma sine T. Okay. I'm not asking what this figure looks like, that you can plot and you can see and so on, but this is the thing. And T is here just all reals, or you can just take close 0, 1. Won't change anything. Okay. So this is the thing. So here is a set. Here is the set S. Okay, and S has a parameterization like this. Okay, S has a parameterization like this. No, so the question that really we are trying to ask in this particular is not this one actually. Sorry. What I'm trying to ask is, can S be defined by an equation? Can S be defined by a polynomial equation, by a polynomial in 3 degrees? Sorry, 3 variables. So the question is, okay, is there a polynomial P x comma y comma z, okay, such that the set of all zeros for the polynomial, the set of all zero, that is, that is a set described by the polynomial, right? The set of all its zeros, set of all, such that the set of all zeros of P is exactly S. That's right. Okay, is there a 3 variable polynomial such that this, a 3 variable polynomial, right? So 3 variable polynomial could be like x plus y plus z. That's a 3 variable polynomial. Yeah, so this is basically, I had discussed this a little bit a few classes back, so maybe that's cool. It's okay. Point is, yeah, 3 variable polynomial here means like this, and then what is the set of all zeros for this, which is a polynomial with all monomials being powers, all powers being positive powers and no square roots and so on. Yes, right. And so what are the zeros for this set? So this, for this one, you see, you can take y to be anything, z to be anything, and this becomes minus y minus z. This is the set of all zeros for this polynomial, right? In place of x, you can put minus y minus z, and in place of y and z, you can put anything y and z. This is a set of all zeros where the y and z varies, right? So that's the example. But the question is, can, yes, surely. The polynomial will not involve any tan theta, right? But the roots, but you're right. No, the roots can involve. So yeah, you can do one more example, 2 variable polynomial. So you can take this polynomial, p of x comma y, right? What are all its roots? Describe all its roots. X comma y is equal to 1. What? That is certainly there, yeah. But you can immediately give me infinitely many solutions: cos theta comma sin theta. Right. I mean, that was obvious. I mean, you didn't see it, but this is obvious, right? Yeah. But the question, yeah. But the question is, okay, no. So, yeah. So in the reals, in the, if I'm allowing x and y to be reals, then these are the only solutions. But if I allow x and y to be complex, then also these are the, no, hold on. No, leave that. That's a different, that will just become. No. What I was asking is that for this cos theta comma sin theta, for this thing where theta is reals, whatever, right? Now, if you turn back the question and ask, what is the collection of all polynomials whose set of zeros is exactly this? So that's a reverse question. That answer is also pretty interesting. Those are, so here is, you can try this. Find all polynomials with zero set exactly, means whose roots is exactly this set S. Certainly any multiples of this will work. Any multiples of this with yeah, so 0 is exactly S. Okay, not exactly S, but yeah, maybe contains S, whose zero set contains S. Basically find all polynomials which will become zero on S. So certainly multiples of this work, but you can prove that there are no other polynomials than multiples of these, and that's an interesting question. That can be framed as a polynomial. Yeah. Huh? Yes, in some sense it is unique. No, two variable polynomials. No, two variable, not three variable. Yeah, then the thing changes. So that's something that you can think about, and that's like that can be also framed as a functional equation problem in polynomials. But yeah. Anyways, let's come to our question. Okay, so here the question is there a polynomial for which the set of all zeros is exactly S? So basically, you see, right? You're imagining a polynomial in which you're imagining just imagine like this, because these kind of questions you can't answer directly, right? You're imagining something like this. Find P. It's like this kind of question. Or show that no P exists, something like that, right? Now this is less of an analysis question, but still it's in the spirit of parameterization. So it's an interesting problem. Could tell him if you can construct, then it is good. Let's see. But you should also notice a little bit here that it's the periodicity of this set that can be a problem. T cos T. So sorry, what should we do for that? No, but how can you write that? That is what one has to prove that, right? But right now it is t is the x and cos t is y, and you want to put z in place of z, you want to put sine t, and you want to get 0, and that you want to happen for all t. That's the challenge. Or maybe I will just make this r. I'm making this r, okay? So once again, the problem is a 3-variable polynomial, and there is hardly anything we know about 3-variable polynomials, right? So once again, you have to think somehow, if you can, and bring it down to 1 variable or something, 2-variable polynomial, something like that. Oh, it's just like the previous, I mean, in the sense that it looks like a problem which is outside the scope, but you can bring it down to the kind of things you know, like 1-variable polynomials. So that is what the goal should be. Maybe that's one way. Basically, I'm saying, yeah. Why not? Why not? It's not bijective certainly, but it's certainly differentiable. Okay, yeah. About okay. Sorry, about this particular polynomial, yes, which satisfies this, right? Yeah, we should certainly do that, and that's how we might get a contradiction, right? So yeah, let's list out the properties. So differentiable is certainly true. That is, it's a polynomial, but is P injective? Anyone? Obviously no, because you're asking for infinitely many roots. You're asking for infinitely many roots, right? So obviously it cannot be injective. But what else can we say? What is P of 0, 1, 0? That's 0. Right? P of and so on. But what should we do so that we maybe, yeah, that's right. Yeah, maybe. So whenever there is cos square and sine square, you have to make it. You can write 1 there. But the problem is there is sort of a periodicity with this polynomial, which is not so polynomial-like. Polynomials are inherently always non-periodic things, right? Polynomials are algebraic things and they are non-periodic, but this has a periodicity problem. And that is what you have to use. Maybe we can do this to completion. No, P is not injective. So we have already said P is certainly not injective. No, because you're demanding that P be 0 for so many different values. So how can it be injective? Is that right? That is, yeah. So almost all polynomials, if they have a root or they have more than one root, then they're not injective. But how can you use the periodicity? So cos t and sin t, right? They are periodic. You have to use that. Yeah, you can try to use that. So maybe I can just write that here. You have cos t and you have cos pi by 2 minus t. And you're demanding that. So remember this, you want to be 0 for all t in R. Yeah, that is the thing. You want this to be 0 for all t, which is possible in the sense that tree variable polynomial can have infinitely many roots. But still there is something about this set which is non-polynomial like. But t is any real number. That's why I've changed this to any real number. I think if it's between 0 and 1, then I will have a problem. Then still the answer is still the same, but the proof becomes very difficult, I think. So what does periodicity mean? Periodicity means that you can fix the range, you can fix the output value and vary the input value. The input value is t. The input is t, and these are the outputs. So is it possible to fix these and vary these? No, some like so that it behaves like a one variable polynomial. So you have to somehow reduce this to one variable case, remember. Yes, right. Yes, yes, exactly. Right. So how can you use that? That's absolutely correct. So that is what you have to use. So you can, so as I put 0, you can also put 2 pi, right? And you will still get 1 and 0, and this should also be 0. And then what? Mm, that's right. So, but now you, if you notice, if you call, you can just call this. I mean, not like this maybe. Let me say like this. You can just call this poly. This is a one variable polynomial. Remember, right? You can call this a polynomial in X. Yeah. Now it was a natural thing to do, right? Because you're seeing this periodicity. You all can already understand. So it's like a one variable polynomial now has to take the value 0 for infinitely many, which is not possible. Yes, yes, that is no between 0 and 2 pi. Yeah, I mean, obviously you could have no, but you could have taken other values also. I think that's what Raghav is saying. You could have taken other values also and done it, but it's fine. You can take 1, 0 and also undo it. Okay. So, but the proof, but there is a slight problem with this proof. Proof is not complete. Please just have a look at it again and try to complete. There is still a flaw in what I've done, but it can be fixed. Okay. Think about that. Think about what is the flaw, just so that you have to do this thing again. And either way, is a new thing, so maybe you should have a look at them again. So yeah, so that this is it. I think let us stop here today. Okay, maybe other questions I can give you over mail later on, which I plan to discuss, and we can discuss them next time. Okay. Yeah. So today we couldn't do much, but I think it's a new topic. Yeah. Tomorrow there will be, hopefully there will be graph theory class. 90% chance yes. If I in case it's cancelled, I'll tell you. Otherwise yes.